Okay, thanks. First, thank Itamar for inviting me today. You promised me it won't be recorded. Thank you. So I would like to talk about our experience with the SSN Bring-up, from risk management to eventually enablement on the actual silicon. So we'll give a quick intro, then we'll talk about the motivation and advantages, go through the implementation, and then the ATE Bring-up. So I'd like to invite Itamar just to give you a quick intro on the SSN.
Okay, guys. Yes, so I will. I want a little bit show time. So I asked OFRI to give the intro. Okay, so what exactly is SSN? For a couple of slides for people that are not aware from SSN. So SSN, it's a data path that is synchronous with n-bit width bus that is used to stream the scanned data in a packet form. And the whole ability to do that, it's actually to allow us to use more data to stream into the design for testing, which will reduce the number of the test time, and of course the cost of it. And what we're actually adding into the design is that we have a SSH, which is the streaming scan host that is used to extract and replace the scan packets and to make sure that we're managing correctly. So if you will see here, this is the SSH itself. And as you can see, we have the streaming, that the input of the bus, and what the SSH is doing is actually synchronizing and replacing the data that is coming from the bus into the EDT, and then doing all the shifting of the data, and then taking out the data that is out in order to test it. So this ability is actually done by the SSH. That's one of the IPs that we're adding. The SSH node is a time slot and pre-programmed by the JTAG network. So as you can see, we're separating between the programming or the test setup of the SSH and the data that is used, and that actually allows us to use 100% of the data stream only for the payload, that all the packets are only scan data and there is no address or control that is being transferred on this SSN bus, and that way we can use more of the bus width for the payload and the test information. As you can see, we have a scan-related signals that are generated inside the SSH. As you can see it over here at the top. So scan enable, EDT update, all these signals are being generated internally, which give us more flexibility in order to control and divide and conquer. And I think OFRI will elaborate more on this topic as well. And maybe this give us that all the activate partition shift and capture independently, which has a benefit for power and timing, of course, from the implementation side. If we will go a little bit into how exactly the packets are being handled. So here we have a short example that, as you can see, we have a bus, SSN bus of 7 bits, and we have 2 cores, core B and core A, okay? And core B has 4 channel in, 4 channel out, and core A has 5 channel in, 5 channel out. As you can see that the total of these two is larger than the bus width. So how exactly the solution is being to handle with that? So if you will take it, like I said, it's a synchronous bus. So let's look at cycle number 1 for this. Cycle number 1, as you can see, we have the input data and the output data. And you can see the first 7 bits will be, first of all, filled with core A. All of its bits, since we have 5 bits for this, will be filled inside the core number A, and core B will get only the 2 bits that are left on the bus. And as you can see, the output, as you remember that we discussed, we're actually synchronizing the input and the output. So in the output side, we have nothing. We will get access since there is no output data to get at that point. Later on, as we will shift into the second cycle of the SSN, which currently, as you can see, the SSN bus could run at a higher frequency than the internal EDT cycles, which give us more capability to actually to drive more data into the design from a test point of view at much higher frequencies. And then, as you can see at the second cycle, we're still not delivering anything on the output, but we're able to fill out the second left 2 bits that are inside the second EDT on core B. and then again we will fill out all the 5 bits of the first instance. And so this is how we're able actually to pre-programmable, and the SSH will know in advance with the state machine which bits is going to which SSH, and that's why we can drive more data into the system, where the system will be pre-programmable on this occasion. And as you can see, when we're starting to drive on cycle number 5, that's where the data will start to shift out as well, and we'll be able to stream out on the same bus the results as well. One more important thing that we can see here, as you can see, all this mechanism of shuffling, we don't really have the ability to see which packet is going to which EDT, and the shift, as you can see, for example here, core number A will shift at the first cycle, while core B will shift only after the second cycle, which you will have all these channels already filled with the data. So this is one of the things that we wanted to show here, that OFRI has a previous experience with Bring-up, and the ability for him to see that not only that we're playing with the data and we're trying to push more data, all of a sudden we want to make sure that the guy that is doing the Bring-up will have good flexibility and visibility of what is going on, and which EDT is shifting, on which data they're seeing on the output. Oh, yeah, so I'll bring it back to OFRI.
Okay, so as Itamar mentioned, our previous mode of work is routing the EDT data, EDT channels, EDT clock, update, and shift clock, and scan enable. Everything is coming from the IO of the package. So instead of that, now everything is going to be handled internally. That's a part of the divide and conquer. So each SSN block is generate those signals internally, so we no longer need to handle that, and that is really the key change here, and why we choose that. So what Itamar mentioned about running packets in parallel, that will eventually lead to a test cost reduction, because we can push more data and use there's a better utilization of the patterns on the ATE. So this is something that we are very interested in. Also, once we are now at the block level, the enablement is much faster. The implementation and integration to the top level is much easier. We don't need to change the top once we change the internal EDT like we had to. And we can now check that on a small design, and then make our assumptions for a better or bigger SOCs. So eventually we took the SSN methodology, and we're now bringing that in other products that we have. Okay, so in architecture, the divide and conquer is really about containing everything to the block level. It's really easy for us to do that, either ATPG and then GLS, the verification. So once everything is contained in the block level, the only thing that is routed out is the SSN data in, data out, and the SSN clock. So the global signals like shift clock and scan enable are no longer global. They are now locally, and we can handle them more easily. So it's either the complexity of the IO routing, and we can use more IO to data instead of control. So we no longer need the EDT update and EDT clock, and also the timing that needs to be done between EDT update and EDT clock is no longer needed. Everything is going to be internally. Even if there is some requirements in post-silicon, we can shift the EDT clock and update internally in the SSN. On the verification side, so we have only one test setup. Previously, we had several configurations of partitions. So we will run 3 blocks together that will optimize the EDT channels and find the best solution of EDT configuration between the partitions. Now we don't need that. We have a single test setup, and we can use that to every configuration, so we don't need to reset and load the different test setup each time that we're going to change the partitions or multiple blocks that we're running together. As I mentioned, the controls and the clocks are no longer generated from the IOs, so they're not global anymore. That's really easy for the verification, so we don't need any top-level GLS with SDFs. It's really going to be handled internally, and that's really a bottom-up verification flow. So block level, we can just verify everything and then go up in retarget. We will only need in retarget to stitch the data between one SSN to another, but we no longer need to verify with SDF at speed patterns, for example, because they won't contribute anything than the bottom, that the block level is going to be showing us. Okay, on the physical design, I think they gained the most. It was a good experience for them also. Much easier for the physical designs now when we have the routing reduction only for data and clock, and it's much easier than balancing scan enable throughout the chip and balancing the EDT clocks and the shift clocks. So when we are now in divide and conquer mode, so everything is at the block level, the controls, as I mentioned, are generated internally. We chose the SSN forward clock implementation. That means that the clock and data are going to route from one partition to another, and we'll have a few pipes, and that means the DSQ FIFOs that will help us balance between partitions if it's a long distance from one SSN to another. By that, we can achieve high frequency for SSN data, and it's higher than the shift data or the scan data. So we can run 100 megahertz shift clock, and the SSN data will be at 200 megahertz or 400 megahertz, depends on the IO limitation. Much easier for them, and the forward clock, although it's a very good solution and a very good method for us, there are some limitations if we are having a complex SoC with a lot of instantiated modules. It's not that easy to keep up the forward clock methodology, but in most cases we could do that. So everywhere we could do the forward clock, we kept that idea. So on the DFT perspective, our experience, so it was very easy for us. The pressure on the top level verification wasn't that severe as we experienced in previous projects. We really got to the top level verification, GLS, we were ready. Everything was playing smoothly, no timing issues between the blocks. So it's easier for the physical design to close 400 megahertz or 200 megahertz data, rather than what they had to do with everything coming out as global signals. The retarget was really an easy thing to do. And since everything is at the block level, the GLS was easier. So once everything is passing at the block level, we are just running SSN continuity and Eagle verify at the top level. There's nothing else to contribute in the top level if you're running with timing. So you're running much faster GLS. So you don't need to run the whole content, because usually GLS at top level is a pain in in runtime, especially if you're running in SDF. Even if you're going to black box all the other modules, it's going to be complicated. And here we didn't have to do that. It was really easier for us to implement. Okay, so on the post-silicon advantages, so because each block has its own phase of shift, they are not synchronized phases. So you'll have each block shift in a different phase. That will help us with the power consumption, because previously we should have kept something, or let's say we should have kept the EDT low power feature for us, low power shift, because sometimes you'll get IR drops if you're going to shift or scan enable the entire design, or you need to change between power domains. You'll have different shift clocks. That's also IO consuming for that. We don't want that. So we have power consumption that is really now attenuated. The debug capabilities are easier because we can have diagnosis patterns ready to be used. It was really easy with SSN to get that. We could isolate the partitions to get just one partition. We don't need special configuration for that, like we had to, we used to say combo configuration when you're running multiple partitions. So now if you want to isolate one, you need to regenerate patterns with only that partition that is running. Also, we have the throttling, like Itamar mentioned, that we're running multiple partitions at the same time. There's also the back annotation, so we can, if there are failures, we can trace back to the patterns really easy. So we chose a robust design, okay, that features data in through a pipe to the SSN host, to another pipe, to the next partition. So this is the forward clock solution. Okay, we decided to go with this to ease up our time enclosure. Okay, so as I mentioned, we added two pipes. We decided to add 2 pipes and ask questions later rather than the other thing. So physical design didn't complain at all. They were really happy with this. So this is how our design looks like. So we're just forwarding everything from one partition to another. Okay, so this, let's say, cloudy logic, okay, that AT the engineers are afraid of. How are we going to properly get out of reset? How are we going to open the security so we can go into scan mode? How are we going to configure the GPIO? So we wanted something to give us an indication for this logic to be enabled. So I used my experience as a test engineer and thought what will help them. So turns out I had one free pad. Okay, so I decided to use that and just going to propagate the SSN clock in throughout the design and then to the SSN clock out. That will, if that will happen and I will be able to observe the SSN clock out on the ATE level, I will know that I passed this obstacle, and now the SSN clock out will show me SSN clock in with a phase on it. Okay, and then I thought, well, there is one signal that goes throughout the design in and out. Maybe I can use it as a shuttle. So I decided to add a mux here, and then I connected in each partition PLL clocks and shift clock. So I will be able to see what is the actual shift inside that I configured, because the internal shift is different than the SSN clock. I can shift in data in 400 megahertz rate, and eventually I will use 50 megahertz shift or 100 megahertz shift. So just to be able to see that the test engineer is using the correct pattern. It's not like open a simulation and look at the waves. So I'm going to use that to see the shift clock in live. So I decided to add this mux. So when I'm running one partition, I will be able, I mean, I'm not interested on what's going out, okay? So I decided to add this. So this mux allows us to have a loop back. So we will have small steps, baby steps to verify each partition. So we'll start with the first partition and then go to the next and the next, going over for all the partitions. So we can now isolate each partition and test it in a standalone mode. And if this one is configured with a loopback, as I said, I don't care what's going out here. So I can configure the PLL mux with IJTAG and select which clock I want to observe, and I can observe that. And the data won't be impacted. So I can still have the same data going out, okay, and be able to observe it. So this is how it looks like on the ATE. Okay, so you can see that it's in reverse polarity, SSN clock out versus SSN clock in. Okay. Eventually, when you are sitting in the this stressful scenario on the ATE in silicon bring-up and nothing works, so you start to blame one each other. So it's the test engineer and the DFT starting to want to understand what's not working right. So when I show them this, okay, we know that levels are fine, timing is fine, also the configuration is fine, but maybe something else is not working properly. So we went and we could eliminate some suspicion debug or suspicion failures here and try to focus ourselves more on the data instead of the configuration. So this really helped us eventually going through. Okay, and here we have a scheme of the PLL observe. Inside we have two dividers. Okay, everything is IJTAG configurable. So we can divide by 2, by 5, or by 10, because the PLLs are at 1 megahertz or 1 gigahertz or 2 gigahertz, much faster than the GPIOs. So in order not to add a divider for each one of them, we decided to add the divider internally. And then if we want, we can use that and lower the frequency to be observed on the GPIOs. Okay.